Hi everybody, Marty Geyer here from your gsp295 class, and I'm going to talk to you this week about hash tables. Hash tables kind of are given a fairly quick gloss over in the textbook, only a couple of quick sections. And I feel they deserve a little more, so I'm going to try to explain it and expand upon it a little bit here. So what hash tables fundamentally are a time-space trade-off. What we've seen so far are a lot of algorithms where you have to make that trade-off between the algorithm. Like in sorting, you can either choose merge sort that's very quick but uses more space, or you can choose a slower sort that doesn't use any space. Trade-offs like that we have to make all the time, implementation details. But with hash tables now we have a trade-off that you can make without changing the algorithm at all, and that is how much space do you want to use to gain better time. So what's particularly striking about hash tables is it's a constant time for all its operations, for inserting, for removing, and for finding are the three central core operations. You put something in, take something out, and find it, which is the same thing as, or removing is the same thing as finding, just with that extra step of removing. So what's particularly interesting is that these all have constant time, so you can do this very, very, very fast, and that should be, at least it's always been to me, very powerful and compelling. And so you have to ask yourself, why wouldn't you just always do this? Well, the answer is, you do it a lot. You do it quite a bit in a number of circumstances. Hash tables are just so terribly useful because they're basically turning an array into a constant time access function for almost anything with a good hash function. And therein lies the key, is the good hash function. So there are drawbacks. You have to come up with a good hash function. It's possible that there may not be a good hash function. Some domains have that problem. If you can't think of a good hash function, or one doesn't exist because of the particular problem you're tackling, then you really just can't use a hash table, because otherwise it will turn into something that won't increase your runtime efficiency. You might be better off without a structure. And also the space consideration. I mean, you do have to start with a significant amount of space. Usually, well, way over ON space, over 2N space or greater, in order to get efficiency out of the hash table. So, if you're talking about 1 million, 2 million items, then perhaps you really can't afford to be creating double the amount of space just to get a time efficiency. And that's really the drawback. So, not a silver bullet quite for everything, but for a lot of things where you really don't have to be concerned about memory, but you want that speed, they are extremely, extremely useful. And I want you to understand it's very powerful. So let's go through a simple example here. So what I have over here are a couple of student IDs, for example. Let's say Marty is 16425. And what we're going to do is pass it through a hashing function. And this is a very simple hashing function. This function is just going to take the modulus of the number by 10 and give the result. And I'm going to explain that in a moment, because I know that's a little confusing to some students. So 16425 modulus 10 comes out to 5. And then we access the fifth element in the hash table, and because it's an array, basically it's a constant time lookup, right? So this is a simple mathematical function, constant time. Get a 5, and now we do just array lookup fifth position, and we stick the item in there. And that's how we do an insert. That's also how we do a find, just reverse that. 16425 passes through the hash function. You get, of course, 5, the same number out. That's one of the important parts about the hash function. It has to be consistent. You can't have a non-deterministic hash function, otherwise this whole thing won't work. So you get 5, go into the fifth position, pull it out. Now usually there are two things. There's a key and there's data itself. In this simple example, perhaps the key is the student ID, 16425, and the data is my name, for example, but it could be any other information, such as a whole record information about myself. So what we stick in here is actually you have to store the key and the data for most situations. You don't actually have to store the key, because you can access the position simply with the key. You don't need to store it. However, when we get to collisions, you'll find out that you actually do. So for most cases, you need to store the key, and it doesn't increase the space that you're using all that much, though it does, but that's just part of the algorithm. Let's see. So another simple example: Jim mapped to 19984, modulus 10, 4. And Frank 41164, maps modulus 4. Now notice these two collide. They're two different student ID numbers, but they have a collision because our particular hash function, which only maps things over 10 items, is going to have a collision, certainly after 10 items, but even before that, when you stick a couple things in, the likelihood of a collision increases. And we'll get to that in a moment, which is the kind of percent of fullness of the hash table. So let me back up now, talk about a couple things before we go forward. The modulus. So I know probably a lot of students, and this is not immediately clicking for you, so let me back up and give this to you. Modulus is a mathematical function. In C and in all computer languages, really, it's indicated by a percent sign. So when you see something percent something, that means you're taking the modulus of it. It doesn't mean you're taking 10% or something like that, like you might think. It's a little non-intuitive until you understand that's the standard notation that everybody uses. So when we write number percent 10, we mean modulus. And what modulus does is essentially chops off values. A very simple example. So when we modulus by 10, what we're doing is we're taking the remainder. Is technically what it's doing in mathematics. It's divising the remainder. So if you divide 16,425 by 10, that's not important what the divisor is. It's going to be 1642, because 1642 times 10 is 16420. But then you're going to have a remainder, and a remainder is 5. And so the modulus is that remainder. And why that's important is because usually when you do things like this by base 10, then it's a chop-off value. So in this case, we just chop it off everything and we take the last digit. And why is that important? That's important because a modulus always gives you a number between 0 and the number you're modulusing it to, because it's a remainder, remember. So you can't have more. As soon as you go over that last position, the divisor increments 1, and the remainder goes back to 0. Right, if you think about it. So when you're dividing and you successfully increment the number, when you get to the remainder of, let's see, example. So dividing by 2, okay? So 4 divided by 2, remainder is 0, and the divisor is 2. 5 divided by 2, remainder is 1. Now 6 divided by 2, again, the remainder is 0 now because you incremented the divisor. 7, remainder is 1. 8, remainder is 0. So you see how this works. It will always alternate between 0 and the divisor itself. So what you have here is a very interesting way to give a space bound, and that's why it's used a lot of times in hash tables, so that's why it's very important to understand, because it gives you the range between 0 and 9 in this case. So this is always, not always, but most of the time, this is going to be the hash table size here that you're modulating by. And in this case, we have a hash table of 10. So I hope that clears that little piece up. We'll talk about it a little bit in discussion, and do ask me, of course, if you have any more questions about it. So that's how modulus works. Now, back to the table percentage filling up. So we have 10 slots in this example. This is a really bad hash table, by the way. You would never really do anything that small, but for the purposes of understanding, it's pretty good. So once we enter in 3 items, we might not get a collision. After 4, maybe not. After 5, our table's half full now. So the odds are, statistically, any random amount, even if our hash table is really good, that we hash in there, we're going to get a collision. And collisions are going to occur because, remember, this is a time-space trade-off. So you're only going to make your hash table so big. You will always have the issue or the possibility, even if it's rare, of colliding. And it's not enough to simply say, oh, well, I'm going to ignore that. You can't. You have to implement some mechanism to handle it. So there are basically 3 ways to handle collisions that I've got down here: linear probing, chaining, and double hashing. And each of these is a separate technique. There's a couple other ones too. These are the basic ones. So let's go through them. So what happens when you hit a collision here for Jim and Frank? They both collide with 4. So we already have Jim written in here. He's in 4 because we did him first. So we inserted him next. First. So insert Frank. We have a collision. So what do? Well, linear probing first. So what happens in linear probing is you simply keep moving until you find an open slot. So you check here, go to 5, that's full too, because we already have something in there. Now we go to 6, and we just stick it into 6. And this is why it's important to store the key, because now you have to do the key when you're doing a find. So go back and do the lookup value. Now when we look up Jim, we get 4. We look it up and Jim's right there. But if we look up Frank, we get 4, and Frank's not there. So we can't assume that whatever we look up will always be there. We have to do a key comparison. So when we get here, we have to look. Is 411164 the same as 9984? No, it's not. So that is not Frank. So then we need to check the next one. Again, not Frank Marty in there, and then check the next one. Aha, I found it. Now notice this screws up things, because now we were going off of a 01 complexity, and now suddenly we have to move over to. And you can see, I think, that if the hash table fills up, you're going to keep moving, and this could actually turn into an ON algorithm. That's really bad, right? We don't want that. That's the whole purpose of doing the hash table, is to get that speed trade-off, or get that speed increase. So a couple things. You can make the hash table bigger, right? But let's not talk about that for a second. Let's talk about what you do in these mechanisms. So, sorry, get myself distracted. So linear probing is moving over. So let's hold the discussion of what you do about it in a second. Let's go through the other mechanisms first, and I'll come back. So chaining. So now what you do with chaining is you simply make a big linked list. And we're going to do a little something like this in the lab. Except we're going to use queues, because we're also studying queues. So now with chaining, we, again, take Frank, hash to 4, get a collision, and now we're just going to make a linked list here. And we'll say, all right, well, we're just going to stick a list here, and we'll stick Frank here, 41164 Frank. And same thing. Now, when we do a lookup, we have to go back in here, and we have to check every item in the linked list. So again, still a problem if you have a lot of entries, entries with relation to the amount of space you have. You could still end up with a very long list with a lot of collisions, and that is, again, bad. Doesn't solve that problem. So double hashing, now the last one. What double hashing is you take a second hash function. Over that for a second. So second hash function. So now we get Frank, collision 4, and now let's just decide we're going to make another hash function that adds 3 and divides by 2. So now 4 plus 3 is 7, divided by 2, knock off the remainder because we don't care, it's 3. And now we put Frank here. And again, we need to store the key, because when we're retrieving, we have to do that same math. This is our second hash function. And you have to be able to find it. So any of these 3 ways are valid ways to handle a situation. None of them really tackle the problem, of course, because the problem is hash table is too small. What's done in practice, I'll give you the practical example a lot, is hash tables auto-grow themselves. So in Java this occurs, C++, you have to do this yourself, of course, when you're implementing, but the way this is commonly done is a hash table, you make it some arbitrary size, whatever you think, 100 elements, whatever, and you start filling it up. And at the point it reaches, I believe it's either 2/3 or 3/4 full is the common academic value. You say, all right, it's too full. The hash table detects that because you store the size, number of elements, in addition to all this. As soon as it's that much full, you go, all right, this is too full. I need to make it bigger. And you just double the size. And this doubling gives you an exponential increase of space usage, but will guarantee that your complexity is O1. Now notice the double in size and wave my hands at it, but that's an O of an operation, or well, at least not with regard to the table size anyways. So if you have a million elements and it's 75% full, and now you decide to auto increase the size of the table, you're going to increase it to 2 million elements. That's a huge jump. So those algorithms are not perfect either, because you have to be careful with the situations in which they're used. That's kind of a standard way to get around the problem of fullness, is just to kind of bump up the size progressively. And that's hash tables in brief. Thank you for listening, and we'll see you next week.